In this video, we'll discuss double infinite sums. Consider again this matrix from episode 5. What is the total sum of all the entries in this matrix? It's an ambiguous question. We saw that if we sum down the rows, we'll conclude each row sums to 0 and that the total sum is 0. But if we sum down the columns, we'll conclude that the total sum is given by the geometric series -1, -1/2, -1/4, -1/8, -1/16, which sums to -2. Denoting the row I, column J entry with Aij, this example illustrates that, generally speaking, the left and right-hand side of this equation are not guaranteed to be equal. And also, this left and right-hand side aren't even the only reasonable ways we might assign meaning to the double sum over all I and j, Aij. We could instead, in a third way, look at partial sums formed by taking squares of increasing size on this matrix. We could define the first partial sum S1 to be the -1 in the upper left, and the second partial sum S2 to be the sum of the 4 entries in the 2 by 2 block in the upper left, -1 plus 1/2 plus 0 plus -1. And we could define S3 to be the sum of the 9 entries in the 3 by 3 upper left block, and continue this way, and then define the total double sum to be the limit of this sequence of partial sums. In general, we could express this by letting Sn equal the double sum over all I and j from 1 to n of Aij. And we don't have any concerns about using this notation for finite sums, because in that setting, addition is commutative. You could interpret this as the two summations placed next to each other with either I equals 1 to n first or j equals 1 to n first, and these are equal to one another. Computing the first few partial sums, in our specific example, S1 equals -1, S2 equals -3/2, S3 equals -7/4, S4 equals -15/8. So the limit of these partial sums is also -2. That happens to be the same as what we got by first adding down the columns. So maybe you conjecture that those two will always be the same, but that should feel very wrong, because by symmetry, if that were the case, then it should also match with adding rows. Like we could take the transpose of this matrix and come up with an example of one where the row sum first matches the square sum, but they differ from the column sum. And these 3 ways aren't the only 3 ways of adding the entries in this matrix. You could come up with more ways. There's infinitely many different ways to do this. Instead of just considering a sequence of partial sums of all the entries in a square of increasing size, we could do this for any rectangle. So instead of letting S sub n be the sum of the entries in the n by n square in the upper left of this matrix, let's generalize this a little bit, letting S sub mn be the sum of all of the entries in the m by n rectangle that's all the way in the upper left corner. Symbolically, we could define S sub mn to be the sum I equals 1 to m, j equals 1 to n of Aij. Now what we were before calling S3 would now be S33, and we could now also refer to other rectangular partial sums that weren't necessarily square. So I could add all of the entries in this matrix in a fourth way by looking at the limit of the sequence S12, S24, S36, S48, etc. And this should feel analogous to rearrangements of series, because each of these different ways of adding the entries is like a different ordering of all of the numbers. We're still adding all of the same numbers, but in some different order. And in that one-dimensional setting, we figured out precisely when that can still have a consistent value and when it won't. 2 videos ago, in our conversation about rearrangements, we proved that if a series converges absolutely, then any rearrangement of it converges to the same limit. And if a series converges only conditionally, then there exists a rearrangement of it that converges to any real number. So we might expect something similar to be true in this setting. And it will be. Our main result here will be analogous to this. If the iterated sum I equals 1 to infinity, j equals 1 to infinity, the absolute value of Aij converges, then both the iterated sum I equals 1 to infinity, j equals 1 to infinity, Aij, and j equals 1 to infinity, I equals 1 to infinity, Aij converge to the same value. In addition, the limit of the Snn is equal to this value as well. So the hypothesis of this is like a 2-dimensional version of absolute convergence. And the conclusion is saying that the 3 main ways we discussed to add the entries all give you the same value. And this is the result we'll prove, but the most general result is even stronger than this. With this hypothesis, any ordering of adding the entries in the matrix will give you the same value. Let's prove this statement. In the same way we defined the rectangular partial sums of our matrix, let's define rectangular partial sums of the matrix of absolute values, letting Tmn be the sum from I equals 1 to m, j equals 1 to n of the absolute value of Aij. So it's adding all of the values in this m by n block in our matrix of absolute values. Our strategy for the proof will be to first focus on those square partial sums Snn and then show as a sequence that they converge. And then we'll argue that both of the iterated sums have to converge to that same value. In order to do this, let's argue that the sequence Tnn converges and use that to show that the sequence Snn converges. So a term Tnn is the sum of all the absolute values in the n by n square aligned to the upper left of this matrix. This has to be an increasing sequence because as n increases, we're just adding more things in absolute value. And we can also argue that this has to be a bounded sequence. Let's argue slightly more generally by this inequality that the Tmn all have to be bounded. So Tmn is equal to the sum I equals 1 to m, j equals 1 to n of the absolute value of Aij, which is less than or equal to the infinite sums of the absolute value of Aij, which is known to converge. So whatever it converges to acts as a bound for all the Tmn. So there exists some real number that's greater than Tmn for all m and n. Now for this part of the argument, we'll just use the fact that that real number is a bound for the sequence Tnn to say that by the monotone convergence theorem, the sequence Tnn converges. Now we could pick some letter to represent its limit, but that won't be particularly helpful to arguing that the sequence Snn converges because Snn doesn't have all of those absolute values. So let's instead just use the fact that the convergence of Tnn implies that Tnn is a Cauchy sequence. And then let's argue that Snn is a Cauchy sequence. Recalling what it means to be Cauchy, there exists some big N in the naturals such that for all m and n greater than or equal to big N, the absolute value of T sub mm minus T sub nn is less than epsilon. And let's visualize in the matrix what one of these differences look like. Because of the absolute value, the order of the difference doesn't matter, but just for this picture in the matrix, let's say that m was larger. So then we'd have an n by n square of values that were being subtracted off of this m by m square. And we're left with this L-shaped region of terms in absolute value whose total sum has to be less than epsilon. But if the total sum of all of those things in absolute value is less than epsilon, by the triangle inequality, if you first took their sum and then took their absolute value, that would have to be smaller, so also less than epsilon. And that's exactly what we need to show that Snn is Cauchy. So returning to the proof, note that for any m and n greater than or equal to n, the absolute value of SMM minus SNN, and this, like we said, is a bunch of those terms from the matrix, all inside a single absolute value, so it's less than or equal to if you had individual absolute values around each of them, and that was equal to the absolute value of the difference TMM minus TNN. So this SMM minus SNN in absolute value is less than or equal to the absolute value of TMM minus TNN. And while there are like two in-between steps that could be shown here, I think the degree to which you'd have to go out of your way to make the notation sensible makes it not worthwhile. Just because specifying which indices correspond to this L shape is just going to be more confusing. But continuing, this was less than epsilon. So SNN is a Cauchy sequence, and thus it's a convergent sequence, so it converges to some limit, let's say S. Now it's this S that we need to show both the iterated sums converge to as well. We argued earlier that the set of TMN, such that M and N are naturals, is bounded above, so let's let B represent the supremum of that set. Just like in a one-dimensional setting, our goal for demonstrating convergence in this two-dimensional setting is to get a handle on the infinite tail, which in this case is some sort of portion of the grid beyond the upper left, extending downwards into the right, either in some sort of L shape, or just as a bunch of columns, or just as a bunch of rows. And we want to find ways to control all of those terms to be less than epsilon or less than epsilon over 2. And identifying this supremum B will allow us to start to do that. We want to argue for convergence, so let's let epsilon be greater than 0. We take an arbitrary epsilon. I want to argue towards a generalization of the statement we have that will allow us to prove the other parts of this theorem. We currently have that the absolute value of SNN minus S can be made arbitrarily small, less than epsilon or less than whatever we want. I'd like that to be true not just for the square partial sums SNN, but for any rectangular partial sum SMN. So I want to show that the absolute value of SMN minus S is less than epsilon. And we'll do this with two parts, making each of them less than epsilon over 2. Because B is defined to be the supremum of the set of Tmn, if we step down by epsilon over 2 to B minus epsilon over 2, we no longer have an upper bound, which means there is an element of the set, say some specific T m0 m0, which is greater than it. Now if we take n1 to be the maximum of m0 and n0, then m and n greater than or equal to n1 implies that B minus epsilon over 2 is less than Tmn is less than or equal to B. The first of those inequalities, because Tmn is greater than or equal to Tm0 n0, because it just has more positive terms. And the second of those inequalities, because B is the supremum. Also, since the sequence SNN converges to S, there exists a big N2 in the naturals, such that n greater than or equal to big N2 implies that the absolute value of SNN minus S is less than epsilon over 2. Let's let big N be the maximum of big N1 and big N2. Now let's consider two arbitrary indices m and n greater than or equal to big N. And without loss of generality, we may as well assume that m is greater than or equal to n. Let's notice that the absolute value of the difference SMM minus SMN in our matrix corresponds to the absolute value of the total sum of all of the first m cells in these columns with index n plus 1 up through m. And so by the triangle inequality, this is less than or equal to the absolute values of each of those cells added up, which is expressed by the difference TMM minus TMN. And by the definition of B as the supremum of all the TMN, TMM is less than or equal to B. So we can continue writing less than or equal to B minus TMN, which is less than epsilon over 2. And the reason we don't need absolute values around the differences of T is because we've taken M to be at least as large as N, and all the T terms are sums of absolute values. Now we can finally write down that statement I was advertising earlier. Observe that the absolute value of the difference SMN minus S, and let's add and subtract SMM and apply the triangle inequality to write, is less than or equal to the absolute value of SMN minus SMM plus the absolute value of SMM minus S is less than epsilon over 2 plus epsilon over 2 equals epsilon. With this established, let's turn our attention toward showing the convergence of the first iterated sum to S. By our hypothesis, the series j equals 1 to infinity aij converges to some real number, say Ri, for each I. In other words, it makes sense to talk about the row sum. So with this definition, I just need to show that the sequence of these row sums, the sequence Rm, converges to S. So let's let epsilon be greater than 0, starting a new convergence argument. Let's choose big N in the naturals, such that the absolute value of Smn minus S is less than epsilon over 2 for all m and n greater than or equal to big N. And we know we can do this by our prior result. In that prior result, our conclusion was less than epsilon, but that was an arbitrary epsilon. And so we can use whatever we want for this new convergence argument. So let's use epsilon over 2. Now let's fix a row index m greater than or equal to n, and consider the rectangular partial sum Smn as a function of n. We can write this out as the sum I equals 1 to m of the sum j equals 1 to n of aij. And that portion in parentheses tends toward Ri as n tends toward infinity. And since this is a fixed finite sum, if we take the limit as n goes to infinity of Smn, we can pass it through the sum and then replace that inside with Ri, expressing this as the sum I equals 1 to m of Ri. And this is just the sum of the entries in the first I rows. Because of this limit, we could take, say, big M greater than or equal to big N, such that for all n greater than or equal to big M, the absolute value of Smn minus the sum of the first mRi is less than epsilon over 2. And this whole choose a big M that's greater than or equal to big N is just kind of another way to express the choosing big N to be the max of a big N1 and a big N2. It just guarantees now that both of these conditions hold, because now when I write for any n greater than or equal to big M, I automatically get that n is greater than or equal to big N. And now we look at the absolute value of the difference of the sum of the first mRi and S, and say that it's less than or equal to, by the triangle inequality, the absolute value of the difference of the sum of the first mRi and Smn plus the absolute value of the difference of Smn and S, and those are both less than epsilon over 2. So the whole thing is less than epsilon. And these sums of the first mRi are partial sums of the series of the Ri. So the series I equals 1 to infinity of Ri converges to S, and replacing Ri again with that series expression it represents, the iterated sum I equals 1 to infinity of j equals 1 to infinity aij converges to S. Now all that's left to do is to show that the other iterated sum that starts with j equals 1 to infinity also converges to S. Our absolute convergence hypothesis, that the sum I equals 1 to infinity, j equals 1 to infinity of the absolute value of aij converges, guarantees that the sum I equals 1 to infinity of the absolute value of aij converges, say, by comparison, just ignoring all the other terms. And this is what it means for the series I equals 1 to an infinity of aij to converge absolutely. And so it converges to, say, some cj, some column sum for each natural number j. Repeating the same argument we made with the Ri, now with the Cj, will demonstrate that the sum j equals 1 to infinity, I equals 1 to infinity of aij converges to S as well. So we've proven the theorem, and we've clarified when it's meaningful to write this infinite double sum notation. If we have that absolute convergence condition, we can use this notation to be equal to that sum S, which is independent of how the terms are added. This is where we'll leave off our discussion of infinite series. We'll be switching gears, and in the next video, we'll discuss sizes of infinity.